Welcome, everyone, to today's deep dive into the world of machines.
Ooh.
We're going to be looking at Shigley's mechanical engineering design today.
A classic.
Yeah, classic text in mechanical engineering for making things that work.
And work well.
Exactly. And, hopefully not collapsing.
I think we can handle that.
Okay.
Shigley's is all about that kind of thing, like blending that creativity with the solid principles of engineering.
I have to admit I was a little intimidated when I first opened it up and saw the equations and diagrams, but it's actually written surprisingly well, I think, for
It is.
even someone like me who's more of a word person than a numbers person.
That's the sign of a great technical text, though, right? It can guide you through these really complex ideas without making you feel lost at sea.
Exactly.
And then they always bring it back around to the real world to show you why
those examples.
things work
Yeah, those are great.
the way they do.
Okay, so Shigley starts off by talking about the design process itself.
Right.
And it's not as simple as just sketching something out on a piece of paper, is it?
Definitely not. No, it really emphasizes that design is an iterative process. So you're going back and forth between, ideas and calculations and refining those calculations over and over again. Yeah. And sometimes you even have to just scrap it all and start over.
Wow.
It's much more of like a dance than a straight line.
So you're constantly going through this loop of having an idea, analyzing it, seeing if it works, tweaking it, and then going back to the drawing board if it doesn't.
Exactly.
Okay.
And, it's not just about making something that functions.
Right.
Design engineers also have to think about the ethics of what they're building.
Ethics. Now we're getting into something a little deeper than nuts and bolts here.
Yeah.
Tell me about that.
Well, think about it like almost everything we interact with on a daily basis was designed by someone.
Right.
Cars, toasters, medical devices, bridges. So designers have to think about all of the implications of what they're making.
Yeah.
So the safety, the reliability, the environmental impact, even the cost.
Okay.
Like you can't just design something cool if it's going to be a hazard or too expensive to actually produce.
Right. You don't want a toaster that explodes when you plug it in or a bridge that falls down when a car drives over it.
Exactly.
So you mentioned cost and materials, and that actually leads perfectly into, I think, what Shigley's talks about next, which is this idea of resilience.
Resilience.
Now, I always thought resilience was like a, personal quality, like bouncing back from challenges. But do materials have feelings now?
Not quite.
Okay.
Not quite. But in engineering, resilience is about a material's ability to absorb energy without permanently changing shape.
Okay.
So like imagine you have a spring, you compress it, and then it bounces back to its original shape.
Right.
That's resilience in action.
So it's about handling stress and strain and bouncing back without being permanently, bent out shape.
Bent out of shape, exactly.
I like that. But how do engineers actually figure out, which materials are resilient?
So there's a lot of science behind that. But one of the key takeaways is that stiffness plays a huge role.
Okay.
And kind of counterintuitively, a less stiff material can actually absorb more energy before it yields.
Wait, really? So sometimes it's better to be flexible than strong.
Yeah, in a way, think about it like this. A steel spring is really stiff.
Okay.
So it takes a lot of force to compress it at all. But an aluminum spring, even if it's the same size and strength as the steel spring, might actually bend a little bit more easily.
Okay.
Allowing it to absorb more energy before it breaks.
So it's like giving a little to avoid breaking completely.
Exactly.
That's interesting.
Yeah.
Okay, so we were talking about aluminum, and I know Shigley's talks about that material quite a bit.
Aluminum is super versatile. It's very strong for its weight.
Okay.
Which is why you see it in things like airplanes and bicycles. And it's also really good at resisting corrosion. So you'll see it in like outdoor applications like window frames and boats.
That makes sense. I've noticed there's also a lot of different ways to process aluminum.
Right.
We see casting, we see wrought alloys, heat treating all these different things.
Yeah, that's because the way you process aluminum has a huge impact on its final properties.
Okay.
So like casting is really good for making complex shapes.
Okay.
While wrought alloys are typically stronger.
Yeah.
And can be shaped by like rolling or extruding them. And then heat treating can change the strength and hardness of the metal.
So you're kind of fine-tuning it to the exact specifications of the job.
Yep, you got it.
Okay.
Right.
So we've talked about materials, we've talked about resilience, but I think it's time to bring on the physics lesson.
Okay, let's do it.
We have to talk about stress. So what do we need to know about stress when it comes to designing things?
Well, Shigley's defines stress as the force distributed within a material.
Okay.
So you can imagine you're pressing down on like a block of wood. Yeah. That force that you're applying is spreading out over the surface area of that block.
Right.
And that's what we call stress.
Okay.
And then a material's strength is basically its ability to handle that stress.
Right.
Without breaking.
Okay, so if I'm designing a chair, for example.
Yeah.
I need to make sure the legs are strong enough to handle the weight of someone sitting down.
Exactly.
Without snapping in half.
You got it. And, the really important thing is to figure out where the maximum stress is going to be. Because that's where that chair leg is most likely to fail.
Okay, so that makes sense. But how do engineers actually go about finding those maximum stress points? Do they just look at the design and kind of eyeball it?
There's a little more to it than that.
Okay.
We have tools and techniques that help us analyze the stress. One of the things that Shigley talks about is something called FEA.
FEA. Now, that sounds familiar. Doesn't that involve computers?
It does.
Okay.
FEA stands for Finite Element Analysis, and it's a really powerful tool that lets engineers simulate how a design will behave under different loads. You can think of it almost like a virtual test lab.
So you can basically stress test your design before you even build it.
Exactly.
And avoid, any catastrophic failures.
Exactly.
That's awesome.
And that's just one example of, the many tools that engineers use to make sure that their designs are safe and reliable.
So we've gone from the basics of the design process all the way to stress analysis. And I think it's clear that there's a lot more to mechanical engineering than meets the eye.
Absolutely. We're just scratching the surface here.
Okay.
Shigley's goes into so much more detail. Right. And it's got a ton of really cool examples that show how these seemingly small design choices can have a massive impact on how a part functions.
I can't wait to get into those examples. But for now, I think we've given our listeners a lot to digest.
Definitely. I hope this has sparked some questions for you about how the objects you use every day are actually designed. And keep those questions in mind as we continue our exploration of Shigley's world.
Welcome back to our deep dive into Shigley's mechanical engineering design. Before we move on, I'm still thinking about those stress analysis examples that you mentioned, where the maximum stress wasn't necessarily where you would expect it to be.
Oh, yes. Shigley's is full of those sort of aha moments.
Yeah.
One that comes to mind is example 3.9.
Okay.
Which looks at the stresses on a beam that has kind of a thin web and then these wide flanges.
Okay.
So kind of picture an I-beam.
Okay, yeah, I can see that.
Okay.
So I would think that the maximum stress would be like at the very top or the very bottom, where the bending force is the strongest.
It seems logical, right?
Yeah.
But here's where it gets interesting.
Okay.
The analysis actually shows that in this particular design, the transverse shear stress is a much bigger factor.
Okay, hold on. Transverse shear stress. Break that down for me.
Sure. So imagine you're trying to slice a loaf of bread with a really dull knife.
Okay.
So the knife is pushing down, but it's also kind of dragging across the bread, right?
Right.
That dragging force is kind of similar to shear stress.
Okay.
And transverse just means it's acting perpendicular to the length of the beam.
So the highest stress then isn't necessarily where the beam is bending the most, but where the shearing force is the strongest?
Exactly.
Okay.
And in this I-beam example, that shear stress is highest right at the connection between that thin web and the flanges.
Interesting.
So it's kind of a hidden vulnerability.
So even if a beam looks really strong from the outside, there could be these weak points depending on its shape and how those forces are acting on it.
Precisely. And that's why thorough stress analysis, often using tools like FEA, is so essential.
Okay, no more eyeballing it. Got it. Now, Shigley's also talks about deflection and stiffness.
Yeah.
Is that related to stress at all?
It's all connected.
Okay.
Think of it this way.
Okay.
Stress is about those internal forces within a material.
Okay.
But deflection is about how much the component actually bends under a load.
Mm-hmm.
And stiffness is basically a measure of how resistant it is to that bending.
So a really stiff component would bend less under the same load compared to one that's less stiff.
Yeah, exactly.
Okay.
And, just like with resilience, a material's Young's modulus, that E we talked about earlier, plays a big role in how stiff it is.
Okay, so material choice is crucial for pretty much every aspect of the design, it seems like.
Absolutely. And here's another important point.
Okay.
Deflection analysis can only be done after you've determined the basic geometry of the part.
Okay.
And that's a little different from stress analysis, which you can actually do section by section.
That's interesting. Why is that?
Well, think about it.
Okay.
The stress at a particular point really depends on the forces that are acting right there.
Okay.
But deflection is about how the whole component bends.
Right.
So you need to know its overall shape and how it's supported.
That makes sense. Now, I noticed Shigley's mentions this Table 7 too.
Oh, yeah.
What's so special about that?
That table is super helpful. It gives these typical ranges of acceptable slopes and deflections for things like shafts, which are rotating components you find in tons of machines.
Okay, so it helps engineers make sure that their shafts aren't bending too much, which could then cause problems for things like gears and bearings.
Exactly.
Yeah.
You got it. If a shaft bends too much, it can throw everything off,
Right.
which leads to wear and tear noise and even failure.
Gotcha. I'm starting to see how all of these concepts are connected. Material choice affects stiffness. Stiffness affects deflection. And too much deflection can mess up your whole design.
Yeah, it's all a delicate balancing act for sure.
Yeah.
And that brings us to another really critical concept,
Okay.
fatigue failure.
Fatigue failure. Does that mean the material gets tired?
Not in the human sense, no.
Okay.
But fatigue failure happens when a component is subjected to repeated loading cycles.
Mm-hmm.
Even if those stresses are below what the material can normally handle.
Okay.
It's like if you keep bending a paper clip back and forth,
Yeah.
eventually it'll snap.
Yeah, I've definitely done that.
So even if a part can handle a load, once it might fail if that load is applied again and again and again.
So how do engineers design for fatigue? Do they just make things super thick and strong to compensate?
That's one approach, but it's not always the most practical.
Right.
Shigley's introduces us to several different fatigue failure criteria,
Okay.
which are these tools that help engineers predict how long a part will last under cyclic loading. So we have things like the modified Goodman diagram,
Mm-hmm.
the Soderberg line, and the Gerber line.
Okay, those sound pretty technical. Can you give us a simplified explanation of what they're all about?
Essentially, these tools help visualize different combinations of stress levels.
Okay.
They take into account, how much the stress varies during each cycle
Mm-hmm.
and what the average stress level is.
Okay.
And engineers can use this information to choose a safe operating range for their design.
So you're basically trying to find that sweet spot where the stresses are low enough that the part won't just fail prematurely from fatigue.
Exactly. And it's important to note that there's no one-size-fits-all solution
Yeah.
here. Which criterion you use really depends on what material you're working with,
Mm-hmm.
how much risk you're willing to take, and even industry standards.
So it's complex, but there are tools and guidelines to help engineers make those decisions.
Exactly.
Okay, it's amazing how much thought goes into designing even the simplest things.
It is.
Now, speaking of how things are put together, we have to talk about fasteners and joints.
Fasteners, the unsung heroes.
Right. Holding everything together.
They are.
So what are some of the key considerations when it comes to fasteners?
Well, first and foremost, it's all about choosing the right bolt.
Okay.
You need something that's strong enough to handle the load
Right.
and made of a material that's compatible with the parts you're trying to join.
Okay. But I'm guessing there's more to it than just picking a strong bolt.
You're right. One really crucial concept Shigley's talks about is preloading.
Preloading. What is preloading?
So preloading is basically about applying a specific amount of tension to the bolt
Okay.
before you actually tighten it down all the way.
Okay, so it's almost like you're giving that joint some extra muscle to resist all of those forces that are trying to pull it apart.
Exactly.
Okay, so what else do engineers need to think about when it comes to fasteners?
Shigley's also talks about this idea of joint stiffness.
Joint stiffness. Is that like a rusty hinge that doesn't want to move?
Not quite.
Okay.
Joint stiffness is basically how much a joint resists deformation when it's under a load.
Okay.
So like a stick joint will barely move even when you apply a lot of force to it,
Mm-hmm.
whereas a flexible joint will bend or deform more easily.
So how does that all relate back to preloading?
Well, it turns out that both the bolt and the parts that are being joined contribute to the overall stiffness of that joint.
Okay.
So a stiff bolt and stiff plates will create a very rigid connection,
Okay.
while a flexible bolt and flexible plates will result in a more flexible joint.
Okay.
And the amount of preload you apply can actually influence that overall stiffness.
So it's not just about choosing the right bolt, it's about understanding how that bolt interacts with the other parts.
Exactly. You got it. And that kind of connects back to the bigger picture.
Mm-hmm.
It shows why it's so important to think about the entire assembly
Right.
when you're designing something, not just the individual components.
You could have the strongest engine in the world, but if it's bolted to a flimsy frame, the whole thing's going to fall apart.
Exactly.
Okay, so we've talked about bolts. What about other kinds of fasteners?
Well, Shigley's also covers things like rivets,
Mm-hmm.
which are permanent fasteners, and even adhesives,
Okay.
which are becoming more and more popular these days.
I am curious about adhesives. When would you choose to glue something together as opposed to bolting it or riveting it?
Well, adhesives are really good for joining materials that are very different,
Okay.
that might be really hard to weld or even impossible to weld.
Mm-hmm.
They're also often used in applications where weight is a major concern.
Okay.
So like aerospace or automotive design.
So it's like super glue for engineers.
Yeah.
But I'm guessing there's a lot more science involved.
Oh, absolutely. Choosing the right adhesive and designing the joint properly is really important to make sure you get a strong and reliable bond.
Okay.
And factors like the surface preparation, the curing time, even things like the temperature and the humidity can all play a role.
This is fascinating. It seems like every aspect of mechanical design has its own unique set of challenges and considerations.
It does, and that's what makes it such an interesting field.
Yeah.
There's always something new to learn and always new problems to solve.
Well, we've covered a lot of ground in this deep dive. We've gone from stress and strain to fatigue failure to fasteners. And it's clear that designing a machine that's both functional and safe requires a really deep understanding of all of these principles.
It does, but beyond the technical knowledge,
Yeah.
there's also this element of creativity and problem solving that makes mechanical engineering so engaging.
It's not just about, crunching numbers and plugging in formulas. It's about using those tools to bring innovative ideas to life.
Exactly.
Yeah.
And I think that's one of the reasons why Shigley's is such a valuable resource.
Mhm.
It provides that foundational knowledge, but it also encourages you to think critically and apply those concepts in new ways.
Well, we've given our listeners a lot to think about.
Indeed.
But before we wrap up this deep dive, there's one more topic that I want to explore.
Okay.
Shigley's touches on these permanent joints, things like welding and brazing.
Right.
Can you tell us a little bit more about when and why you would use those techniques?
Of course. So permanent joints are typically used when you need a connection that's going to last, essentially the lifetime of the product.
Mm-hmm.
So you see them a lot in applications where strength and rigidity are really important.
Okay.
So like in bridges and buildings and heavy machinery.
Okay, so welding is for ththose heavy-duty applications.
Exactly. And there are all these different types of welding techniques,
Yeah.
each one suited for specific situations. And Shigley's goes into all the detail there, explaining how factors like, what type of metal are you welding? How thick is that material?
Mm-hmm.
How strong does that joint need to be? All of those things influence which method you're going to choose.
Welding seems like such a complex process. Is there anything else engineers have to consider?
Oh, absolutely. One critical factor is what we call the heat affected zone,
Okay.
or HAZ for short.
EHAZ.
So welding involves these really high temperatures,
Mm-hmm.
and that heat can actually change the properties of the metal around the weld,
Mm-hmm.
making it more brittle or prone to cracking.
So it's not just about making a strong weld. You have to make sure that the surrounding material can handle that heat as well.
Exactly. Engineers have to carefully consider that HAZ.
Okay.
And sometimes they even take steps to minimize its impact, like preheating the metal
Mm.
or using special welding techniques.
That's amazing how much thought goes into even these seemingly simple things.
It is.
Now, what about brazing? How is that different from welding?
So brazing is kind of similar to welding in that it uses a filler metal to join those two pieces together.
Okay.
But the key difference is that with brazing, the filler metal has a lower melting point than the metals that you're trying to join.
So it's almost like a gentler form of welding?
In a way, yes. It creates a really strong bond, but you're not actually melting the base metals,
Okay.
which can be a good thing depending on the application.
Right. Okay, so we've got welding for high-strength permanent connections. We've got brazing for a gentler approach. But we haven't really talked that much about adhesive bonding yet.
Yeah.
Where does that fit in?
So adhesive bonding is becoming more and more popular.
Mm-hmm.
It basically involves using a special adhesive to bond two surfaces together.
So it's like super glue for engineers.
Kind of.
Yeah.
But the adhesives that are used in engineering are much more advanced than what you would find
Yeah.
in your typical household glue.
Right.
That they can withstand really high temperatures and pressures
Mm-hmm.
and all sorts of crazy environmental conditions. And they can create these incredibly strong and durable bonds.
Okay, so when would you choose adhesive bonding over welding or brazing? What are its advantages?
One major advantage is that you can use it to join dissimilar materials.
Okay.
So things that would be really hard to weld or braze, like metal to plastic, ceramic to composite materials.
Interesting. So it opens up a lot more possibilities.
Yeah. It's also often preferred when weight is an issue.
Okay.
So like in aircraft or automobiles, Adhesives tend to be much lighter than welds or brazes.
Okay, so it's lighter and it can join different materials. Those are some pretty compelling advantages.
They are. But like any joining technique, adhesive bonding does have its limitations.
Okay, like what?
Well, one key consideration is the strength of the bond.
Okay.
While modern adhesives are super strong, they don't always match the strength of a weld or a braze, especially in really high-stress situations.
So it's important to choose the right adhesive for the job.
Exactly. And the surface preparation is super important.
Okay.
Those surfaces need to be clean and properly treated to make sure that the adhesives can actually form a strong bond.
So it's more to it than just slapping some glue on and pressing things together.
It is.
It seems like pretty much every aspect of mechanical engineering involves a lot of planning and a lot of calculations.
You got it. And really understanding the materials you're working with.
And all those forces.
And that's what makes it such a challenging and rewarding field.
Okay, so last time we were in the middle of talking about all this fastener stuff and preloading bolts and how important that is.
Right.
You were explaining that it helps prevent the pieces from separating under load.
Exactly.
Which could cause all kinds of problems.
They can. Yeah, if you just tighten a bolt without preloading it, you risk those parts coming apart.
Right.
Even slightly. And that tiny little gap can cause vibrations and loosening and all those things you don't want.
Right.
Even fatigue failure.
So it's about creating a really tight seal?
Yeah.
That prevents any movement?
Yeah, that's a good way to think about it. It's all about creating that clamping force to hold everything together nice and snug.
But how do you know how much to preload it?
That's a great question. Over-tightening is definitely something you want to avoid.
Right.
You can damage the bolt or the parts. And that's where torque wrenches come in.
Okay.
Really helpful tools.
So you're applying the right amount of torque?
Exactly. They let you apply a very precise amount, which then translates to the tension in the bolt.
So it's all about finding that right balance.
It is.
Too much or too little could be a problem.
Exactly.
Yeah.
And Shigley's actually goes into detail about how to calculate that preload for different bolts and materials.
Well, there's a lot of math behind it.
There is.
Okay.
Yeah, but that's part of what makes mechanical engineering so interesting.
Right.
All of these forces and materials and calculations, they all work together to design even the simplest parts.
Okay.
And speaking of those calculations,
Yeah.
Shigley's talks about this concept of joint stiffness.
Joint stiffness.
Which is related to preloading.
Now, when I hear joint stiffness, I think of a rusty old door hinge that doesn't want to move.
I could see that. But in this context, it's really about how much that joint resists deformation.
Okay.
So think about it. A stiff joint won't move very much, even when you apply a lot of force.
Right.
But a flexible joint will bend or deform more easily.
Okay.
So it's a measure of how solid that connection is.
Right. But how does that relate to preloading?
So both the bolt itself and the parts that are being joined, they both contribute to the stiffness.
Okay.
So if you have a stiff bolt and stiff plates, you get a rigid connection.
Okay.
But if you have a flexible bolt and flexible plates, you end up with a more flexible joint.
Gotcha.
And that preload that we talked about can actually influence that overall stiffness.
So it's all connected.
It is. It all works together.
Yeah.
And that kind of connects back to what we were talking about earlier.
Yeah.
About how important it is to think about the whole system,
right?
Not just the individual parts.
Okay. No, we were talking about different types of fasteners.
Right.
We talked about bolts. And you briefly mentioned gaskets.
Oh, yeah, gaskets.
Which seem like they're pretty small, but they play an important role.
They are. They're kind of those unsung heroes.
Yeah, and keeping everything sealed up and leak-free.
Exactly.
What are some of the design considerations, then, when it comes to gaskets?
Well, the material's really important.
Okay.
You need to pick a material that can withstand the temperature and the pressure of whatever environment it's going to be in.
Right.
So, for example, a gasket in a high-pressure steam line is going to be made of something very different than a gasket that's just sealing a water pipe.
Right, of course.
But the material isn't the only thing.
Okay.
The shape of the gasket is also important.
Okay.
And how much you compress it. You need enough pressure to get a good seal, but not too much.
Right. You don't want to crush it.
Exactly. And Shigley's actually provides some guidance on how to calculate that optimal compression force.
It's amazing how much science goes into something as simple as a gasket.
It is.
Okay, so we've talked about gaskets, but I know there are other ways to join things permanently.
Right. We got things like welding and brazing.
Yeah, permanent joints. When would you choose something like that over a bolted connection?
So permanent joints are usually used when you want something to last
Okay.
for the lifetime of whatever you're building. You see them a lot in like bridges and buildings,
Okay.
places where strength and rigidity are really important.
So that makes sense for like a bridge
Well,
support beam or something.
And there are a bunch of different welding techniques
Mm-hmm.
that are used in different situations.
Okay.
And Shigley's goes into all the details about, which metals can be welded together, how thick the material is, all that kind of stuff.
Welding just seems like such a complex
It
process.
can be.
Is there anything else that engineers have to consider when they're designing a welded joint?
Yeah, there's one thing called the heat affected zone.
The what?
The heat affected zone,
Oh, wait,
HAZ.
HAZ, okay.
But basically, welding creates these really high temperatures, and that heat can actually change the metal around the weld and make it more brittle or likely to crack.
So it's not just about making a strong weld, it's about making sure that the area around the weld
Exactly.
can witstand the heat too.
You got to, and sometimes engineers will take steps to minimize that impact.
Mm.
Things like preheating the metal
Yeah.
or using special welding techniques.
Okay, so brazing, how is brazing different?
Brazing is kind of similar
Okay.
in that it uses a filler metal
Mm-hmm.
to join the pieces.
Okay.
But the filler metal has a lower melting point than the metals being joined.
Okay.
So it's good for things that are maybe a little more delicate.
So it's a little bit gentler.
It is, yeah. It creates a really strong bond, but you don't actually melt the base metals themselves,
Right.
which can be good in certain situations.
Okay, so welding high strength, brazing a little gentler.
Mm.
And then there's adhesive bonding, which we haven't talked too much about.
Adhesive bonding is becoming very popular. It's basically using a special adhesive to glue things together.
Okay, is that like super glue?
Kind of, but the adhesives that engineers use are much more sophisticated.
Right.
They can handle all sorts of crazy environments, and they can create super strong and durable bonds.
So when would you choose adhesive bonding over welding or brazing?
Which is really good for joining dissimilar materials.
Okay.
So things that are hard to weld or braze,
Yeah.
like metal and plastic, for example,
Okay.
or, ceramic and composite materials.
So it opens up a lot of different possibilities.
It does. And it's also really good in applications where weight is a concern.
Okay, like airplanes.
Exactly like in aircraft or cars.
Yeah.
Adhesives tend to be a lot lighter than welds.
Okay, so it's lighter. It can join different materials.
It can.
Sounds pretty good to me.
But of course, like anything, it has some limitations.
Okay. Like what?
Well, one big one is the strength.
Okay.
Modern adhesives are incredibly strong, but they might not be as strong as a weld, especially if you're dealing with a lot of stress.
Right. So it's about choosing the right adhesive for the job.
Yes.
Yeah.
And making sure those surfaces are prepped properly so that you get a really good bond.
It seems like every aspect of mechanical engineering requires so much, planning and calculation and really understanding the materials.
You got
and
it.
all the forces involved.
That's what makes it such a fun and rewarding field.
Well, I have to say, this deep dive has given me a new appreciation for all the work that goes into designing. All these machines and structures,
I'm glad to hear that.
from the tiniest little gasket to the biggest weld, it all has to work together perfectly.
It does.
So to all our listeners out there, next time you see a machine or a bridge or something, take a moment to appreciate all the thought and effort that went into making it work.
Absolutely.
So until next time, keep those gears turning,